Sunset crater behind me rises about 1,000 feet. It is your typical cinder cone. It is made up of basaltic tephra from a fountain eruption, probably a very short-lived one, maybe 3 hours, 3 days a week. These eruptions of basalt usually let off much of the earlier gases so that the following eruptions are breakout at the base lava flows, basaltic flows. We'll see some of those basaltic flows in a moment. Fountaining eruptions and basalt flows, as we see at Sunset Crater, are not the only type of volcanism that occurs on the planet. On a recent trip to Italy, I had the opportunity to hike up the flanks and to the crater of Mount Vesuvius, an active volcano above the Bay of Naples. When you look around, you do see basaltic lava flows. Layer after layer of volcanic rock has built up this volcanic edifice. But when you take a close look at the layers, they're not basalt. Some of them, like the top layer here is, but that gray layer that you see in the middle, that is andesite. It tells us something very important about volcanic constructs, that they're not made all of the same kind of volcanic rock because they don't all come from the same kind of magma. And this dictates the properties of that particular volcanic construct and the volcanism that follows. In 79 AD, probably the most famous eruption of Vesuvius occurred when it wiped out the Roman port city of Pompeii in a catastrophic eruption that included a pyroclastic flow that buried the city, leaving it as a snapshot in time. I had the opportunity to visit Pompeii with an archaeologist who was part of the restoration team. And it is very impressive when you see the extent as they uncover it layer by layer out of the ash. But more impressive to me is that that active volcano sits above the Bay of Naples, and in its shadow, millions of people in the Naples metropolitan area. Both a reminder of the awesome destructive power of the Earth's internal heat engine and how it acts to shape planet Earth. To understand the nature of volcanism and volcanic processes, you have to first understand volcanic eruptions. Volcanic eruptions are all driven by pressure release of the dissolved gases within the magma itself. These dissolved gases, called volatiles, drive volcanic eruptions. And as we can see, volcanic eruptions vary in both style and explosivity. Volcanic eruptions are very much like what happens in the locker room of any of your favorite teams after winning a championship. The champagne comes out and it erupts everywhere. Champagnes erupt for the very same reasons that volcanoes do. Pressure, when the cork is in, holds the carbon dioxide that is a volatile, a gas dissolved in the champagne, until the cork comes out and the pressure is released. And then the volatiles within the champagne, that is the carbon dioxide, drives the eruption. Now, unlike an eruption of champagne, we're going to see that magma is driven by volatiles more than carbon dioxide. Carbon dioxide is a very, very distant second to the number one volatile, which is water vapor. So it really is the water vapor within magma that drives the eruption. Now, one thing we see when there is a number of people out uncorking champagne is that they'll cover the front of the champagne bottle with their thumb, causing it to erupt even further. What they're doing is resisting the flow. And by resisting the flow, they're taking the pressure and allowing it to build up. Well, there's a property in any liquid called viscosity, which is the resistance to flow. So the more viscosity a magma has, the more explosive the eruption because it can build up the pressure. So when we look at eruptions, the things to note is they are driven by volatiles. The explosivity is related to both the volatile content as well as the viscosity. And what we're about to see is that will determine all of the volcanic products, including landforms. When we think of volcanic products, what do you think of first? I think for most people, what they think of is lava. And lava is indeed one of the important products of volcanic eruptions. Most lava flowing on the Earth's surface today is basaltic. But not all basalt is created equal. Lower viscosity basalt flows almost like water, and it creates a kind of volcanic rock that the islanders of Hawaii refer to as poihoi. More viscous basalt flows tend to be very blocky in texture, and chunks roll down the front, and it moves very, very slowly. This is referred to by the native islanders as a'a. Lava flows can present a real hazard to anything in their way. But lava flows also act to construct parts of the crust of the Earth. At mid-ocean ridges, lava flowing on the seafloor creates pillow basalts. The oceanic crust itself is made up of layer after layer after layer of pillow basalt. Sometimes it gets scraped up on the continent, and we can see these pillow basalts, remnants of oceanic crust, as fragments along continental margins. So there seems to be, from everything we've seen so far, some relationship to the magma chemistry, the type of the magma, and what we see both in terms of eruptions and products. So we could break all magma and lava that occurs on the planet into sort of three distinct categories. Basalt or mafic magma, andesitic or intermediate magma, and rhyolitic or silicic or felsic magma. And usually we use the terms basaltic, andesitic, or rhyolitic to actually refer to the lava of that magmatic composition. What you see here is what really is the difference chemically between these magma is the ratio of silicon to oxygen. Yes, oxygen. We think of oxygen in the air that we breathe, but it turns out that oxygen is the major elemental component of the crust and mantle of the Earth. It's the most important element making up the silicate minerals. Number 2 on that list is silicon. The ratio between the two in the magma governs and dictates everything. And by the way, the density also varies because iron and magnesium content within the magma inversely varies with the amount of silicon relative to oxygen. But these drive some important properties that we've already seen. Remember, the two important properties in volcanic eruptions were viscosity and volatile content. It turns out as the silicon-oxygen ratio of the magma increases, so does the viscosity. That is, the resistance to flow. So felsic magma builds up pressure within it very quickly and can have very explosive volcanic eruptions as a result. Basaltic magma, mafic magma on the other end, has a very, very low viscosity. So it tends to build up less pressure, driving its volcanic eruptions. This in turn will drive whether or not you have lava flowing on the Earth's surface or tephra. Tephra is pyroclastic material, that's ash and dust and volcanic fragments. The result of explosivity in volcanic eruptions. The more effervescent to explosive the eruption, the more tephra that is generated. And by the way, the double whammy of felsic magma and intermediate magma is the volatile content also varies with the silicon-oxygen ratio. That is, the innate water vapor inside a magma ranges from about 4 to 6%, increasing as you increase in silicon-oxygen ratio. So in turn, the greater the silicon-oxygen ratio, the more likely you have explosive eruptions, and the more likely you are to form tephra. I am going to add one caveat to that, and that is, if water gets added to magma, like basaltic magma, even though it's normally not explosive, you will get an explosive eruption from it because of the addition of the increased water to the system. Now, we just spoke of tephra, which is another volcanic product. The amount of tephra is going to depend on how effervescent or explosive the eruption was. Tephra, or pyroclastic material, includes ash and dust. In fact, most of it is ash and dust. These are very fine-grained particles that are less than 2 millimeters in size. And they're generally dominated by broken glass shards, microscopic broken glass shards. But they can vary in the amount of broken crystals and lithics, which are rock fragments. Lapilli and cinders are pea to walnut-sized particles. These are 2 to 64 millimeters. Blocks and bombs are anything that are greater than that. The difference being that a block is just a volcanic fragment, a broken rock that gets thrown out in a very explosive eruption. But a bomb is magma that is a blob during flight and cools. And because it cools during flight, it becomes very streamlined and becomes almost like a football when it crashes back into the earth. This is ash and dust, and you will find it pervasively after major volcanic eruptions. Lapilli and cinders. Most people are familiar with cinders, and the larger fragments there are lapilli. And then finally, we're looking at a bomb. A bomb, when it first lands, as it forms in flight, it will not only be this sort of aerodynamic football shape, but it would have a long tail, maybe 2 to 3 times the length of what looks like a football here. The tail, because it's always made up of a glassy material, shatters on impact, and what we're left with is this football-like fragment that we refer to as a volcanic bomb. The origin of tephra is pretty plain whenever you watch a volcanic eruption. This is a fountaining eruption on a vent on the island of Hawaii. It's effervescent, and even though it's basaltic, there are gases running the eruption, and the early release of gases from the basalt gives you this effervescing fountain eruption. And you can see the dark materials from the spatter around and the cloud forming around it. That's tephra. This is also tephra. This is from the eruption of Pinatubo. That entire cloud is ash, dust, volcanic fragments, bombs, blocks. And that's the other source of tephra, is though most of it is from the magma cooling very quickly and explosively being distributed, some of it is from the explosion breaking up pre-existing volcanic materials as well. Now, we can have pyroclastic clouds, that is eruptive clouds made up of pyroclastic material, but one of the great hazards of very explosive volcanic eruptions is what you see here. What you're looking at is a pyroclastic flow. And that pyroclastic flow is a mixture of hot, and at night we can see it glow in many cases, almost incandescent to incandescent particles that are suspended in hot air. So it moves like a fluid down the surface of the volcanic construct at about 200 kilometers per hour. This is incredibly destructive and has resulted in huge loss of life. And this is a mummified citizen of Pompeii, preserved forever in the pyroclastic material that erupted in 79 AD. Pyroclastic flows are one of the most deadly and dangerous of explosive eruptions. Now, we've said that volatiles are driving this. These are the dissolved gases. So gases, in turn, are part of volcanic eruptions. In fact, when a geologist says volcano, unlike what most people in common usage of the language are thinking, we're not necessarily thinking of some mountain that erupts. Technically, a volcano is a vent in the Earth's surface through which lava and associated tephra and gases erupt. Essentially, it's a hole in the ground. It's the crater itself. Volcanic constructs, which people refer to as volcanoes, are volcanoes. There are volcanoes there, but a volcano is any place where we have this vent in the Earth's surface through which we get eruptions of lava or tephra or gases or a combination of those. Now, the gases that are in a lava and get released are the volatiles that are driving the eruption itself. Water vapor is the major constituent. It's all about the water vapor. Carbon dioxide is an incredibly distant second. And nitrogen compounds and sulfide compounds make up a very small percentage, only a few percent. They make up 100% of the smell, as water vapor and carbon dioxide are odorless, colorless gases. The sulfide compounds, especially hydrogen sulfide, results in a very pungent smell people commonly associate with volcanic areas. Now, as we're talking about gases, I don't want you to confuse this with hydrothermal activity. Hydrothermal activity occurs anywhere where you have groundwater in contact not with the magma itself, but with rocks that have been heated up by the magma. Groundwater flows into these areas where the rocks are heated by magma and then in turn is heated and comes back out at the surface. These are incredibly dangerous places, though. They are filled with hot pools and vents and boiling mud pots. Their heat is something that people understand, and they can be so hot as to scald you. The other problem with a hydrothermal vent is the pH, that is the chemistry, can range from acidic to caustic, depending on the rocks and the minerals that are chemically being leached by the hot waters running through them. In areas where we have hydrothermal activity, we can have hot springs that are comfortable enough to literally sit in and enjoy, but never, ever, ever approach a hot spring without knowing in advance that it is okay for a human being to be there. They can either be so hot that they can take your life, or either so acidic or caustic that you won't last but a moment stepping into it. In some places, like in Yellowstone National Park, the hydrothermal activity in the area can be witnessed in something called a geyser. A geyser is a hydrothermal area with very special plumbing underneath. The plumbing underneath allows for the buildup of bubbles within a chamber, and the bubbles block a very tiny vent, making it to the Earth's surface. So that allows pressure in the hydrothermal system to build up, and then when the pressure overcomes the resistance from the clog, they erupt out. They can do this with some regular basis because after the eruption, that chamber underground fills again with groundwater. So places like Old Faithful, even though you can't set your watch by it, do have regular eruptions because of that mechanical system, and it's all about the plumbing. The other thing we think of when we think about volcanic products is volcanic landforms. And we look at volcanic landforms in terms of relief. The term relief technically means the difference in elevation between a high point and a low point. So with volcanic landforms, what we commonly think of as a volcano truly is a positive relief feature. You'll hear me use the term a volcanic construct to distinguish that from a negative relief feature, which would be a crater or hole in the ground, something with negative relief. Let's first look at volcanic constructs or positive relief features. We've seen so far that the silicon-oxygen ratio, that little bit of variance in the chemistry, determines everything about volcanism. It determines the volcanic eruptions. It determines the type of material that's produced. It also determines the volcanic constructs that are produced. We will look at volcanic constructs now through the window and lens of the chemistry of the magma from which they form, specifically looking at how the increase in the silicon-oxygen ratio dictates not only the volcanic processes, but the construct itself. We will start with basaltic or mafic lavas. Lava plateaus occur formed on the continent where you have flood basalts. Flood basalts are when wide swaths of the Earth's crust kind of open up at the surface and fissures form with basaltic lava, very fluid basaltic lava, flowing over hundreds of square kilometers. We do not see this occurring today. We do see fissure eruptions, and let's not confuse the two. We get fissure eruptions at many volcanic constructs. What's different about the formation of a lava plateau and flood basalts, the flood basalts are fissure eruptions occurring over hundreds of square kilometers. They do involve very fluid, low viscosity basaltic lavas. A good example would be the Columbia River flood basalts up in the Pacific Northwest that cover not only the Columbia River Gorge, but much of southeastern Washington state and northeastern Oregon and parts of Idaho. We also find flood basalts technically occurring at mid-ocean ridges, but they're not going to form lava plateaus per se. A major volcanic construct that we see on the planet are shield volcanoes. Shield volcanoes are called shield volcanoes because they look very much like an ancient Greek shield on its side, very, very broad with gentle slopes. These are formed from basaltic lava as well, fairly fluid basaltic lava from a point source rather than from an area opening up with lots of fissure eruptions. Because it's basaltic lava, mostly mild eruptions and pretty large volumes of basalt. Again, the shield volcano, when we look inside of one of these, is made up of layer after layer after layer of basalt. A good example is Mauna Loa on Hawaii. Cinder cones are also made up of basaltic lava, but these form from the first eruptions of basalt in an area where it's fairly effervescent still. The first pressures being released being greater than the pressures driving later lava flows. It is built entirely from ejected basaltic lava in the form of tephra. And although we call them cinder cones, they have pyroclasts of various size, from cinders and lapilli, making up the broadest part of the cone itself, to large fragments, blocks and bombs that fill the throat of the crater. Sunset Crater in Arizona is a really good example of a typical cinder cone. These form in hours, days, weeks, and are fairly short-lived, and usually their eruption is followed by the eruption of lava flows breaking out from the base. We commonly see these in fields, in other words, fields of other cinder cones forming in the area, one on top of the other. And that's certainly what we see in the area of Sunset Crater. These are formed from fountaining eruptions that allow for tephra to fall close to the vent, forming up the typical steep-sided structure that we call a cinder cone. Cinder cones tend not to be very tall features. They get up to 1,000 feet in some areas, and compared to something like a shield volcano, which could be the entire size of the island of Hawaii, what we're looking at is a drastically smaller kind of construct. The classic volcanic shape most of us think of are composite volcanoes. A lot of times they're referred to as stratovolcanoes, although truly a stratovolcano is one form of composite volcano. It's the most typical form. These structures are made up of alternating layers of lava flows and pyroclastic flows. And these interbedded lava flows and pyroclastic flows form a shape that is more gentle at its base and steeper towards the crest, giving it a very sort of convex upward shape. Mount Fuji in Japan and Mount St. Helens are a couple of really good examples of composite cones around the world. Here's a photograph of Arenal in Costa Rica, which I took a few years ago. You can see the very typical volcanic cone shape, and you can see how it steepens towards the crest. This is also true in the Cascade volcanic chain in the Pacific Northwest. This is looking back at Shasta from Oregon towards California. And even though the crest has been eroded a bit by glaciation, and you have a parasitic cone, that's Shastina, growing out of the flank of Mount Shasta, it is one of the typical composite cones of the Cascade volcanic chain. I mentioned Vesuvius earlier. Vesuvius is a type of composite cone called the Somma stratovolcano, where a smaller cone, which you can see sort of on the right, is growing out of the volcanic construct that used to be there that had blown apart in an earlier eruption. And to the left, you can see the outer ramparts of that earlier construct, which would have been much taller. The cone you see is the modern active volcano, and it is the one that erupted in 79 AD. Mount St. Helens, which erupted in 1980, is a beautiful example of a composite cone, although this particular stratovolcano wasn't the largest in the Cascade range. It was about 9,000 feet at its crest before the 1980 eruption. It lost several thousand feet of its crest post-eruption. But it gives us an example in that eruption of the hazards associated with composite volcanoes. And I did want to take a moment just to review them. You can get violent eruptions of these composite cones due to the fact that they are composed of mostly intermediate to silicic lavas. Mostly these are andesitic lavas. And once you get past basaltic lava, there is enough viscosity and enough pressure built up for pretty violent eruptions. Commonly, they can produce a pyroclastic flow, which we mentioned before is a fire mixture of toxic gases and volcanic particles. They can move down the slope at up to 200 kilometers an hour. The eruption of a composite cone, such as Mount St. Helens, has other impact and effect. One is the creation of a lahar, which is a boiling mud flow. And when you look at a picture like this, it's not hard to understand how it is that a boiling mud flow could result from a volcanic eruption. The crest of the high Cascades of the Pacific Northwest have not only snow on the top, but have glaciers that have formed over time. A lot of water is locked up in those glaciers, and when a volcanic eruption occurs, it only takes a few seconds to melt all of that water under very, very high heat conditions and have it mix with all the loose tephra to form boiling mud. The boiling mud will run down the slopes after a volcanic eruption. Here's the eruption in Mount St. Helens, showing the blast and the volcanic pyroclastic cloud forming above. The blast not only took out much of the surrounding area, it completely wiped out the forests that were surrounding Spirit Lake next to Mount St. Helens. All of the debris goes into the boiling mud flows so that we not only have lahars but debris flows inundating places like the Tuttle River adjacent to the Mount St. Helens area and Spirit Lake. And here we can see how mud flows have inundated the margins of the Tuttle River and how it had impact on structures in the area. The aftermath of Mount St. Helens not only gives us a reminder that these structures can be very, very hazardous, but that there is an ongoing and continuous evolution to volcanism. When we look at Mount St. Helens and how much it's changed over time, from the May 18, 1980 eruption onward, today we look at Mount St. Helens, and growing from the inner crater is a volcanic dome. The last vestiges of the magma that was feeding this eruption has changed chemistry once again, increasing the silicon-oxygen ratio. Volcanic domes are bulbous masses of congealed, degassed lava that is very, very silicic or felsic in composition. That means it has the highest silicon-to-oxygen ratios. We do see these commonly as resurgent domes following a volcanic eruption, a massive volcanic eruption. At Lassen, what we see is after a major volcanic eruption in prehistoric times, the last lavas to come through the area are felsic or silicic in composition, forming this very, very bulbous mass we refer to as a volcanic dome. Typically, these structures are circular in shape with a low profile. They can also be cylindrical spires that are so viscous that they just kind of come erupting straight out of the earth. These areas, because we're talking about very silicic lavas, in some cases andesitic, but for the most part silicic or felsic in composition, they're very explosive and potentially very, very hazardous. What we see is that the properties of the volcanic constructs, the type of eruptions they have, the products that are formed, everything about volcanism is dictated by the silicon-oxygen ratio. Understanding the volcanic processes on planet Earth is about looking into that idea of differing magmas. We'll talk more about that in a moment. What I'd like to do is move from looking at these structures sort of individually and making some comparisons. Now, I'm comparing first in this profile a Mauna Loa in Hawaii, which is a shield volcano, with Mount Rainier. Now, Mauna Loa and Mount Rainier both stand at about 14,000 feet above sea level. The difference is Mount Rainier is 14,000 feet building off the continental platform. Mauna Loa is 14,000 feet building off the seafloor, which is 22,000 feet deeper. So the total construct is huge by comparison. Now, not all shield volcanoes are huge. The point here is they can be. The Hawaiian Islands are made up by a congealing of multiple shield volcanoes forming each of the islands. Now, when we compare something like Mount Rainier to Sunset Crater stands about 1,000 feet. So you can see that there's a huge difference in the size of those structures. Composite cones can be smaller than 14,000 feet. We saw Mount St. Helens at 9,000 feet. They tend to be fairly tall constructs. Cinder cones, on the other hand, vary in size, but usually don't get much taller than about 1,000 feet. And we've been talking about positive relief landforms. Now let's take a moment to look at negative relief structures. Negative relief means that you're looking at a hole in the ground. You're looking at something where volcanism has caused a depression rather than built up a volcanic construct. And the most important of these is something called a caldera. Let's define a caldera. A caldera is a negative relief feature or a depression formed by expansion during volcanic eruptions. So if you think about it, this depression at the top of Mauna Loa has been formed by the fact Mauna Loa kind of swells before volcanic eruptions, and it erupts and it comes back and it swells. But during the swelling phase, it's expanding, causing the roof of the volcano itself to drop down. This is a caldera. So one of two ways calderas can form. Remember, caldera by definition means a collapse feature associated with volcanic eruption. That collapse can be by volcanic eruptions in an ongoing sense in the summit of shield volcanoes. And we find summit calderas in a number of locations. But the collapse structure can be from a catastrophic volcanic eruption itself. This is Crater Lake in Oregon. And yes, it's a misnomer. It's really not a crater, it's a caldera. A crater is simply the vent in the Earth's surface through which eruptions are occurring. This is a caldera, a collapse structure from a volcanic eruption. This is Wizard Island. You can see this parasitic cone has grown out of the middle of Crater Lake. And it gives us a little bit of understanding of the formation of Crater Lake. This is a digital bathymetric model of Crater Lake. Digital bathymetric models are like digital elevation models, except we're looking under the water. But you're looking at Crater Lake, a nearly circular feature, fairly steep-sided, with a couple of parasitic cones that have grown. One is Wizard Island, which you can see on the left breaching the surface, and it's sitting on a platform of what are pretty obvious lava flows that are now covered by water. But how did this feature form? If we were to go back in time nearly 10,000 years ago, instead of Crater Lake, at this location in the volcanic chain that we know as the Cascades, we would see a mountain that geologists today refer to as Mazama. And this volcanic construct went through a catastrophic eruptive phase, resulting in Crater Lake. And it starts with the eruption itself. During an eruption, the cork has come out, the magma is shooting through to the surface, lava spilling out, in this case, lots of tephra is flowing out on the Earth's surface. During a catastrophic eruption, much of the magma chamber can empty. Well, when the magma chamber is filled with magma, it's holding up the crust above it. But if you get a significant emptying of the magma chamber, something like 50, 60, 70% of the magma chamber, what follows is the crust above collapses. And you guessed it, it causes additional pressure, causing the volcanic eruption to get even bigger. Over time, the entire area has collapsed mostly into the magma chamber. There's some residual magma in that magma chamber. The eruption finally finishes, and what you're left with is a caldera, here, Crater Lake. The residual magma can feed small volcanic constructs like Wizard Island, which we call parasitic volcanoes that have formed from the residual magma. Now here we're showing in this with the catastrophic eruption of a volcanic construct, and this can happen, and does very commonly happen. But we can also get much bigger calderas. This is looking at the Long Valley caldera from space. It is an incredibly big feature, similar to what we see in Wyoming with the Yellowstone caldera. It's a very large area of the Earth where there's been volcanic eruptions in the past, where ring fractures have opened up and much tephra has flowed across the Earth's surface. These areas are capable of massive, massive explosive volcanic eruptions. And the calderas are there as a testimony to the volcanic activity and how it shaped the Earth in those locations. An eruption of Long Valley caldera or an eruption of the Yellowstone caldera could be quite catastrophic in terms of the amount of eruptive force and the amount of tephra put into the atmosphere. Now here we're looking at another hole in the ground. This is Ubehebe crater in Death Valley. Ubehebe crater in Death Valley is an example of a maar. A maar is not a caldera. It's a very, very different kind of construct. And if you look at the beige and reddish layers in most of the surface exposed in the crater, what you're looking at are sedimentary rocks, not volcanic rocks. Around the rim of the crater, you will notice gray and black tephra. Those are volcanic rocks, and it speaks to the origin of these features. We talked about hydrothermal activity before, and we mentioned how in hydrothermal activity, the water isn't in contact with the magma. That is, groundwater is in contact with hot rocks that are in contact with the magma, not directly in contact with the magma. What would happen if the magma actually breached the water table? Well, what you would get is something called a phreatic eruption, which is all of that water flashing to steam instantaneously. And by the way, that would cause an expansion within the rock itself of over 300%. That would be very explosive. And that's what you have here, is the crater left from a single phreatic eruption, a very momentary explosive event that might have only taken a few seconds to form. We're talking a lot about structures, and we see that eruptive behavior and the type of volcanic construct or the negative relief feature you have is dictated by the chemistry of the magma. But what governs that? Is there some clue to how the silicon-oxygen ratio of a magma is dictated and what governs it? And it's in part governed by the tectonic setting. What you're looking at are the possible tectonic settings where volcanism can occur. Now, if you remember from our lecture on the tectonic framework, you can have volcanic eruptions at divergent margins, and you can have them at subduction zone settings, a type of convergent margin. And we can also have intraplate volcanism. Intraplate tectonic settings means we can have volcanism not associated with a plate boundary. So that's three different types. And if you think about it, these different types can either occur in oceanic crust and lithosphere, or they can occur in continental crust and lithosphere. And we want to look at the variation of magmas that form there. At a divergent margin, magma is formed by the partial melting of the asthenosphere because at divergent margins, the lithosphere is thinning. Thinning the lithosphere puts less pressure on the asthenosphere, and as the pressure is lowered on the asthenosphere, the melting point of the silicate minerals that make up the ultramafic asthenosphere results in a partial melt, forming basaltic magma. In an oceanic setting, remember that oceanic crust is made up of basalt. The basaltic magma works its way through and forms lava flows on the seafloor. At mid-ocean ridge, we have basaltic volcanism, resulting in lava flows underwater and the creation of pillow basalts. It's always basalt flows and basalt volcanism at mid-ocean ridges. And we can see that preserved in the geology where oceanic fragments have been scraped up onto the margins of continents. In continental rift valleys, the divergent process is going to be a little different because the setting is no longer an oceanic setting, but a continental setting. So when we have a divergent margin in a continent or a continental rift valley, we get what is referred to as a basalt rhyolite association. Still, basaltic magma is what's formed from partial melting of the asthenosphere because you've lowered the pressure. The pressure is lowered through thinning of the lithosphere. That magma coming up will either give you basalt flows or, by interacting with the continental crust, which we've learned before in this class is already silicic or felsic in composition, if that gets melted in, then it's going to go very quickly to a rhyolitic magma. So we get what is referred to as a basalt-rhyolite association, and that doesn't mean the intermediate magmas in the middle are absent. That can happen. It just means that it's dominated by basalt or rhyolite. Another location in which volcanism occurs is at subduction zone settings. And the volcanism that occurs at subduction zone settings doesn't vary much between ocean-ocean convergence and ocean-continent conversion. The convergence of oceanic lithosphere with either a continental plate or an oceanic plate results in subduction. The subduction process forces the oceanic lithosphere with oceanic crust and wet oceanic sediments down into the asthenosphere. That process adds wet sediment to the asthenosphere, and the addition of water to the asthenosphere lowers the melting point. And the mafic silicate minerals, that is the high iron magnesium rich silicate minerals, partially melt in the asthenosphere because of that introduction of water and the lowering of the melting point. Partial melting of the asthenosphere yields basaltic magma. So what we get here is an interesting case where above subduction zones, volcanic arcs are formed, very similar to what we see in the Cascade Range. We do note that the entire Circum-Pacific region, with the exception of parts of the transform boundaries we see in Western North America, is all subduction. It is referred to as the Ring of Fire because most of the world's explosive volcanic activity occurs at these locations. We would say that in volcanic arcs above subduction zones, what we are looking at is a basalt andesite rhyolite association where andesite dominates most of the life of the arc. And this is kind of interesting because we see the early formation of volcanic arcs are dominated by basalt, then andesite takes over, and then rhyolite kind of comes in at the end, both at the life of the arc, but in terms of volcanic centers like Mount St. Helens or Shasta or Lassen. All of these are witnessing a variation over time of the silicon-oxygen ratio in the magma. So again, subduction zones are a very, very special setting where we see basalt andesite rhyolite associations, where andesite dictates most of the volcanic expression of the volcanic arcs over the life of the arc. This means we're going to get composite volcanoes, various forms of stratovolcanoes and others, along the length of the arc. That doesn't mean those are the only ones we're going to find. We'll also find cinder cones. We certainly will find volcanic domes, especially resurgent domes here. But most of the volcanic arc, such as the high Cascades, will be dominated by composite cones from andesitic lavas. And finally, the final tectonic setting has to do with intraplate volcanism. This is volcanism that is occurring not at a plate margin. And these are the result of hotspots or mantle plumes deep in the mantle that have risen and pinged on the lithosphere and burnt a hole. Commonly, such as what we see in the islands of Hawaii and the Hawaiian chain, we get hotspot tracts that form above them. And what do we see in places like Hawaii? So Hawaii would be a hotspot in oceanic setting. And it's very similar to what we see with mid-ocean ridge volcanism. Though the chemistry is a little different. The silicon-oxygen ratios are the same, and we get basalt, partial melting of the asthenosphere, giving us basalt flowing out onto the ocean floor and forming new crust. We get shield volcanoes forming from these point sources, and most of the volcanic islands associated with hotspots are shield volcanoes in their nature, and they can be quite large and have grown from the ocean floor. And though we've seen a lot of hotspot activity and discussed it in earlier lectures with regard to the Hawaiian Islands in the Hawaiian chain and then the Emperor Seamount chain, that volcanism, which is purely basaltic, is not the only thing we see associated with hotspot activity. In an oceanic setting, it will be all basalt all the time. But like continental rifting, when you have a hotspot on the continent, the basaltic magma welling through the continental crust can interact with the continental crust, and the chemistry can change. And what we get is a basalt rhyolite association. Basalt rhyolite association means you get basalt flows and basaltic volcanic processes occurring on the continent. But you can also get rhyolitic features, such as volcanic domes and very, very explosive eruptions. And this is one reason that the volcano at Yellowstone, this huge caldera, is so important as a potential hazard at some point down the road, is because it can have a massive eruption of felsic lavas. Now, of course, when we say basalt rhyolite association, just as we did with rift valleys, it doesn't exclude in some places having intermediate composition magma and having andesitic volcanism. Whether basaltic, rhyolitic, or even andesitic volcanism in an area like Yellowstone, it is a constant reminder of how powerful the volcanic processes are that can help to shape the Earth. They are part of a set of processes that not only relate to the Earth's internal heat engine, but the overprinting of superficial processes that act to shape landforms. Standing here at Sunset Crater, we are reminded that volcanic processes and other geologic processes we've been studying, like earthquakes, mountain building, can alter the landscape, can be recorded in the landscape. Join me next time as we go on to look at superficial processes. These are things like weathering, erosion, and deposition, not powered by the Earth's internal heat engine, such as the processes we've been looking at, but powered by the sun itself.